Hello, my name is Jonathan Apostle, and this is my third lab for Physics 2212. The goal of this lab was to measure the magnetic field of a bar magnet to determine its distance dependence. Some key assumptions that we made in this model is that we are treating the bar magnet as a perfect dipole and assuming that a uniform Earth's magnetic field. This is going to help us with our calculations. Just to preview the conclusions, when observing this, we noticed that there was a power law, so the magnetic distance will approach a -3. Here are some fundamental principles and equations that are necessary for this. I'm going to be explaining each of these equations in detail. So for the first equation, this is the Biot-Savart law, and this shows how the magnetic field is dependent on the distance and the orientation. So in other words, the dB would be the infinitesimal magnetic field contribution from an infinitesimal amount of the magnet, and the r hat is the unit vector, r squared is the distance, and the mu naught value is just the permeability. The next equation is the distance formula, and this is necessary because it demonstrates that the strength is inversely proportional to the distance. So this was described earlier as that power rule thing. And then for the third equation, this is an expression of the energy field of a magnet. And again, it's going to be basically the same as an electric dipole. Here are those equations one more time. Here was the experimental setup. So for materials, we had the bar magnet, the effect sensor, which was that app we downloaded on our phones, and then the meter stick, and then finally the computer to record the measurements. So I simply just measured and recorded the distance and then based that in the table provided. Some key assumptions for this are that the magnet will act as a perfect magnetic dipole, the Earth's magnetic field will be uniform, and that there will be that power law present. In other words, that distance will matter. So here's the system and surroundings. So the system is going to be the sensor on the phone, which is described as that red X, and the surroundings is everything else, including the magnet and the magnetic field of the Earth. All right, and one quick thing as well. This is going to be the same exact thing when we're doing those off-axis measurements. In other words, we're still considering the system to be this red X, so the sensor on the phone, and the surroundings are everything else, as previously described. So here are the measurements for the on-axis field, and then here are them for the off-axis field. And then here's the graphical expression that was already calculated for me within that table. So what did we observe with our measurements? So as the sensor was further away, the magnetic field gets closer to 0. And this makes sense considering that law we were talking about previously. And then additionally, as it moved closer, the sensor that is, the magnetic field would increase. Therefore, the position had an impact on the strength of the field. So now, with this information from the graph, I can calculate the mu value. So the red will be the slope of the graph. When I'm referring to the graph, it's this thing. I can then find the value. It's important to note additionally that I just considered this nearly -3 because it would be such a small amount. And then I could then put the y-intercept into this part of the equation, and then from there I can solve to get the dipole moment. All right, so the glow script code just is going to simulate the magnetic field, which is generated by this bar magnet. So as you can see, I have the constant. This is just established from class, and then I was able to calculate the dipole field, and then I was able to then just visualize this. And I did the same exact thing, by the way, for the off-axis field as well. So this is what it looks like when it's run. And just to be clear, the values that I got were from the table. Now we can look at our conclusions for both the glow script code and then the tables for the values we collected. So as seen in the data, the collections do somewhat line up with our expected results. So we observed a magnetic field about 5.57 times 10 to the -5th. However, the expected field, so the stuff from the glow script code, was 5.7 times 10 to the -5th. So what caused this difference? Well, it was probably due to human error, so basically just not reading the scale correctly. However, the values were so small that I honestly don't think they're very significant. Now looking at the what if and what does it mean scenarios. For the first scenario, what would happen if you hadn't aligned your setup with the Earth's magnetic north? So this would just mean that the measured magnetic field would no longer be the same or in the same direction as the Earth's magnetic field. So it wouldn't be orthogonal, meaning that you could measure a combination of Earth's and the magnetic field. So this is just going to distort it and it's going to make it inaccurate. For the second one, what if there were two magnets end to end? Well, we know that there's going to be the strength would increase, and this is because there's a dipole moment and you're going to basically double it. In other words, you're adding two fields together, so therefore the strength is just going to increase. I like to always provide a brief summary for all of the things that we went through in this lab. So the purpose was to just measure the magnetic field as a dipole, and then we're going to relate this to a computational model and then the actual values that we observed. This is relating back to the Biot-Savart law. A key assumption is we remember to align the magnetic fields. Again, the system was a sensor of the surroundings for the magnet on the Earth. The methods are described in detail, but we just measured the strength at different distances, often on the axis. And for the results, we decided that there was a power rule. So basically, as you went further away, the strength of the magnetic field will decrease. And then this was confirmed with our experimental results.